Hello everyone, myself Dr. NCH Ramgopal, working as Associate Professor in Mathematics in the Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. I welcome you all to today's session on Analytic Function, Part 2. Today, I am going to discuss some problems on Analytic Function and Harmonic Function. In the last session, we have discussed about an Analytic Function and the conditions to check the analyticity of a given function, which are called CR equations or CR conditions, then harmonic and conjugate harmonic functions. Conjugate harmonic functions. Now, what is an analytic function? For example, we have a function f of z and the derivative of f exists for all z in a neighborhood, epsilon neighborhood of some z naught. Then the function is said to be analytic at the point z equal to z naught. And to check this, first we write the function f of z in the form of u plus iv, where u is the real part and v is the imaginary part. Now we check the CR conditions. Now what are those CR conditions? First find dou u by dou x, dou u by dou y, dou v by dou x and dou v by dou y. That means the partial derivatives of u and v with respect to x and y. First find all these first order partial derivatives of u and v with respect to x and y. Then if dou u by dou x is equal to dou v by dou y and dou u by dou y equal to minus dou v by dou x, then the function f of z is said to be analytic. So these conditions are called CR conditions or CR equations. If f is in the form of u plus iv and u and v satisfy the CR conditions, then the function is said to be analytic. If these conditions fails, simply we can say f of z is not analytic. And also we have discussed about harmonic function. A function u of x comma y is said to be harmonic if it satisfies the Laplace equation. Laplace equation. What is the Laplace equation? Del square u equal to 0. And this del square is called the Laplacian. So this del square is called the Laplacian operator given by dou square by dou x square plus dou square by dou y square. So if dou square u by dou x square plus dou square u by dou y square is 0, then the function is said to be harmonic. So these concepts were discussed in the last class. Now today I am going to solve some problems on analytic and harmonic functions. Now coming to the first problem, show that the function f of z equal to e power z is analytic everywhere in the complex plane. So here given function f of z is e power z and we know that z is in the form of x plus iy. Z is a complex variable, x plus iy. So that implies f of z will be e power z e power x plus iy, and by simplifying this we get e power x into e power iy. Now there is a standard notation. So we know that e power I theta. What is the expression for e power I theta? Cos theta plus I sin theta. So this is well known to all. E power I theta is cos theta plus I sin theta. Using this, we can expand this e power iy. So f of z equal to e power x into e power iy can be written as cos y plus I sin y. Now let us simplify this again. E power x into cos y plus I into e power x into sin y. So which is in the form of u plus I into v. This is u and this is v. the real and imaginary parts of f of z. Now, to check whether the function is analytic or not, or to prove that the function is analytic, we need to prove that u and v satisfy CR conditions. Now, what are those CR equations or CR conditions? Dou u by dou x equal to dou v by dou y, dou u by dou y equal to minus dou v by dou x. So, for that reason, we need to calculate all the partial derivatives of these u and v with respect to x and y. So, we have u equal to e power x cos y. Now, what is dou u by dou x? We are differentiating partially with respect to x. So, that means we have to treat other independent variables as constant. So, here cos y is the other independent variable. So, by treating cos y as constant, we need to differentiate this e power x. The result is e power x again. So, e power x into cos y, since cos y is constant. And dou u by dou y. Now, with respect to y, we are not changing, we are differentiating partially with respect to y. So, we treat x as constant. So, keep this e power x is constant. Now, differentiating that cos y, we get minus sin y. Next, what is v? E power x into sin y. So, dou v by dou x is e power x into, we treat sin y as constant and e power x derivative is e power x. Dou v by dou y equal to, now e power x is constant, sin y derivative is cos y. Let us denote this by equation small 1 and this is small 2, this is 3 and this is 4. Now, from 1 and 4, it is very clear that from 1 and 4, you can see here, 1 is dou u by dou x, 4 is dou v by dou y. Now, dou u by dou x is equal to dou v by dou y. Dou u by dou x is equal to dou v by dou y. And from 2 and 3, you see here, 2 is dou v by dou y equal to minus e power x sin y, whereas 3 is dou v by dou x is e power x sin y. So, from 2 and 3, dou u by dou y is minus of, I can replace this term by dou v by dou x. So, both the CR conditions are satisfied. Hence, so here u and v satisfy CR conditions. Therefore, f of z, the given function f of z is analytic. So, like this, by finding the partial derivatives of real and imaginary parts and using the CR conditions, we can check whether the given function is analytic or not. So, here in this particular example, the given function is analytic since u and v satisfy Cauchy-Riemann conditions. Similarly, another problem, here f of z is sin z and we have z is x plus iy. So, f of z will be sin x plus iy. Now, which is in the form of sin a plus b, and all of you are familiar with those trigonometric formulae. So, here sin x plus iy, sin a plus b, sin a cos b plus cos a sin b. Here, again using a known result, we have cos iy is equal to cos hy and sin iy is I sin hy. So, using this result, here I can simplify this as cos iy is cos hy plus cos x into sin iy. Sin iy is I sin hy. So, cos x sin hy. Now, which is in the form of u plus iv, where u is the first function sin x into cos hy, v is the second function cos x into sin hy. Now, let us check whether u and v satisfy Cauchy-Riemann equations or not. To check that, first we need to find the partial derivatives of u and v with respect to x and y. Now, first u is sin x into cos hy. Now, the first one is dou u by dou x with respect to x. So, we treat the other independent variable as constant. So cos hy is constant. And what is the derivative of sin x? That is cos x. So cos x into cos hy. Next, dou u by dou y. Now sin x is constant. The derivative of cos hy is again sin hy. For hyperbolic functions, we get both positive itself. Similarly, v is cos x into sin hy. Now dou v by dou x. The derivative of cos is minus sin into sin hy, and derivative of v with respect to y partially with respect to y. So cos x as it is, and sin hy is cos hy. Now from the above equations, it is clear that dou u by dou x cos hy, dou v by dou y cos x cos hy. So dou u by dou x is dou v by dou y. The first condition holds. Dou u by dou y is sin x sin hy. Dou v by dou x is along with minus sin x sin hy. So, and dou u by dou y is minus dou v by dou x. That means u and v satisfy the Cauchy-Riemann conditions. Hence, the given function f of z equal to sin z is analytic everywhere. By finding the partial derivatives and by using Cauchy-Riemann conditions, we can check whether the given function is analytic or not. And here there is another problem similar to the previous, but here the problem is to find the value of k such that the function is analytic. So it's not necessary to prove that, or the question is not to prove the given function is analytic. Here the function is having an unknown k. So you see here k cos ky and sin ky. So we need to find the value of k such that the function is analytic. Under the assumption that the function is analytic, we need to find the value of k. So first, given f of z is e power x cos ky plus I sin ky, and let us simplify this first. E power x into cos ky plus I into e power x into sin ky, which is in the form of u plus iv, where u is e power x cos ky and v is e power x sin ky. Now, a function f of z is said to be analytic if CR conditions holds. That means if u and v satisfy CR conditions, it is analytic. Already here in the problem, we need to find k under the assumption that the function is analytic. So that means dou u by dou x must be equal to dou v by dou y, and dou u by dou y equal to minus dou v by dou x. Let us find dou u by dou x first. Okay, sorry. Let us find dou u by dou x first. E power x into cos ky as it is, dou u by dou y minus k e power x sin ky. The derivative of cos is minus sin, and we need to find the inner function derivative. So this k comes. Next, dou v by dou x, e power x derivative is e power x itself, sin ky is constant. Dou v by dou y, k into e power x into cos ky. The derivative of sin ky is k into cos ky. Now, using the CR equations, here dou u by dou x must be equal to dou u by dou y, since the function is analytic. So dou u by dou x e power x cos ky is equal to dou u by dou y, k into e power x cos ky. So here the LHS function is present on the RHS also as a product with that k. So this happens only when the value of k equal to 1. Similarly, if you compare the second condition also, you can prove that k equal to 1. Hence, if we take the value of k as 1, then this function will be analytic. Now coming to the next problem, here this is a problem on harmonic function. Show that the given function u is harmonic. Now first, when a function ux, y is said to be harmonic, if this is the solution of Laplace equation. Now what is that Laplace equation? Del square u equal to 0. That implies dou square u by dou x square plus dou square u by dou y square is 0. So if the sum of these second order partial derivatives is 0, then the function is said to be harmonic. Let us find the second order partial derivatives. Let us find the second order partial derivatives of u. So first given u is e power 2x into x cos 2y minus y sin 2y. Now let us find dou by dou x first, partially with respect to x. So here we have e power 2x, and again here also it's a function of x, so uv rule we need to apply. First function into derivative of second function with respect to x, so cos 2y constant, x derivative 1 minus, it is completely a function of y, and we are differentiating with respect to x, so we can put 0, derivative of constant is 0, plus this is u v dash. Now u dash v, what is the derivative of first function? 2e power 2x into second function, right as it is. Okay, now that means e power 2x cos 2y plus 2e power 2x into x cos 2y minus y sin 2y is the partial derivative of u with respect to x. Similarly, here we need to find the second order partial derivative. So again differentiating with respect to x, we get dou square u by dou x square. Now again with respect to x, cos 2y constant, and derivative of this is 2e power 2x cos 2y constant plus, now again uv rule, 2 into e power 2x into first function into derivative of second with respect to x, so cos 2y constant, and again here 0 plus, now derivative of first, so 2 into derivative of e power 2x, again one more 2 comes, so 4 e power 2x into second function as it is. So we need to simplify this first. So 2 e power 2x cos 2y plus 2 e power 2x cos 2y plus 4 e power 2x x cos 2y minus 4 e power 2x y sin 2y. So this is equal to 4 e power 2x cos 2y plus 4 e power 2x x cos 2y minus 4 e power 2x y sin 2y. This is equation number 1, which gives the second order partial derivative of u with respect to x. Similarly, we need to find the second order partial derivative of u with respect to y. But first, what is given u? E power 2x into cos 2y into x minus y sin 2y, x cos 2y minus y sin 2y. Now let us differentiate this partially with respect to y. So e power 2x constant. Now the derivative of this function with respect to y. So x constant, derivative of cos 2y is minus 2 sin 2y minus, here we need to apply uv rule because we have the product y into sin 2y. So y into 2 cos 2y, the derivative of second function, minus sin 2y into derivative of y is 1. This is e power 2x into minus 2x sin 2y minus 2y cos 2y minus sin 2y. So this is dou by dou y. Now to find the second order partial derivative of u with respect to y, again differentiate partially with respect to y. So we get dou square u by dou y square with respect to y. So e power 2x is constant, minus 2x is constant, derivative of sin 2y is 2 cos 2y minus, here I need to apply uv rule. So 2 into derivative of y is 1, so cos 2y as it is. Now minus derivative of cos 2y is minus 2 sin 2y. So already we have minus 2 sin 2y. So this becomes plus 4y sin 2y. And again with respect to y here, minus 2 cos 2y. Now after simplifying this, we get this 2 into 2 minus 4 e power 2x x cos 2y. And here minus 2 cos 2y minus 2 cos 2y. Total minus 4 cos 2y. So minus e power 2x into 4 cos 2y plus e power 4 into e power 2x into y sin 2y. So this is equation number 2. Now adding 1 and 2. Now let us check whether by adding 1 and 2 whether we get 0 or not. Now let us go to the previous one. 4 e power 2x cos 2y. Here we have, here also this is with minus sign. So for both, here we have, here 4 e power 2x cos 2y and minus 4 e power 2x cos 2y. So these two gets cancelled. So dou square u by dou x square plus dou square u by dou y square is, so this term and this term gets cancelled. Next, 4x e power 2x cos 2y and minus 4x e power 2x cos 2y. So this rectangle, the term in the rectangle, these two are with opposite signs. Next, the last one, minus 4y e power 2x sin 2y plus 4y e power 2x sin 2y. Obviously, we will get del square u is 0. That implies u is harmonic. The given function is a harmonic function since it satisfies the Laplace equation. So like that, by finding the partial derivatives, we can verify whether the given function is harmonic or not. Coming to the next problem, again we need to check whether the function is harmonic or not. The given function is 4xy minus 3x plus 2. Let us find dou by dou x with respect to x, 4y minus 3, dou square u by dou x square, the second order with respect to x. But here there is no x term 0. Dou u by dou y now with respect to y, 4x, and here there is no x, there is no y term, so constant 0. Dou square u by dou y square, again it is a function of x, so we get 0. That implies dou square u by dou x square plus dou square u by dou y square is 0. That implies del square u equal to 0. So u satisfies the Laplace equation. U satisfies the Laplace equation. Hence, u given function u is harmonic. And coming to the last one, find the value of k such that the function is harmonic. This problem is also similar to the third problem that we have discussed in analytic function. Here, we need to find the value of k under the assumption that the given function is harmonic. That means the given function satisfies Laplacian equation. So, given f is x cube plus 3kxy square and f is harmonic, that is given, or we need to consider that f is harmonic, and using that condition we need to find k. That implies del square f is 0. That implies dou square f by dou x square plus dou square f by dou y square is 0. So one by one we need to find. F is x cube plus 3kxy square. So dou f by dou x 3x square plus 3ky square, and again differentiating with respect to x, here we get 6x and there is no x term here, so 0. And dou f by dou y, the first term is completely having x, so it is constant 0. 3kx constant with respect to y, 2y we get. So 6kxy. Now dou square f by dou y square, again with respect to x, 6kx. Since f is harmonic, del square f must be 0. That implies dou square f by dou x square plus dou square f by dou y square is 0. So 6x plus 6kx is 0. This is possible only when, if I take k equal to minus 1, 6x minus 6x gives 0. So the value of k is minus 1. If we take k equal to minus 1, this function will be obviously harmonic. In today's session, I have solved some problems on analytic and harmonic functions. How to check whether the given function is analytic or not, whether the given function is harmonic or not. To check the analytic nature, we need to check the CR equations. Whereas to check whether the function is harmonic or not, we need to check whether the function satisfies the Laplace equation or not. For both concepts, we need partial differentiation. So if you know how to find the partial derivatives, it is very simple to check whether the given function is analytic or not, or harmonic or not. In the next session, we are going to discuss two methods to find the analytic function in which any one of real or imaginary parts is given. For example, f of z equal to u plus iv. We will have only u. Now find v. If we have u, we need to find v. Similarly, sometimes imaginary part will be given, we need to find the real part. So, if real part or imaginary part, only one is known to us, we can evaluate the other part also, and not only that, we can directly find the analytic function f of z. So, we are going to discuss about those two methods in the next session. This is for today's session. Thank you very much.